Okay, so while you're going through and practicing these problems, I strongly suggest maybe do the problem on your own, then pause the video, watch my explanation, see if my explanation matches up with what you did. So number one, find the indefinite integral of the fifth root of x to the ninth. And so this problem gets at the idea of the power rule. So we are going to write this as x to the 9/5. So x to the ninth, but you're doing the fifth root of that. So that's x to the 9/5 power. So if we're doing the antiderivative of x to the 9/5, we know we add 1 to that exponent, and then we divide by that exponent. And so this becomes x raised to the, if we add 1 to 9/5, 9/5 plus 5/5 would be 14/5. And then we'd be dividing by 14/5. But a lot of times I don't say divided by 14/5. I say multiply by 5/14. So our solution here should be 5/14 x to the 14/5, and then don't forget the plus c. And so that would be solution A. Number two, find the indefinite integral and check the result by differentiation. So what this problem is getting at is, let me go back to number two. What this problem is getting at is when you have a single term in the denominator like that and multiple terms in the numerator, you can take each one of those terms in the numerator and put it over that denominator separately, or individually. So this looks like this. This is the same thing as the antiderivative of 3u squared over u to the fourth plus 4u over u to the fourth minus 12 over u to the fourth du. And again, this is du because we have a function in terms of u right here. And so we've got a little bit of work to do. We've got some simplifying before we even do the calculus side of things. And so this is equal to, let's write this as 3u to the negative 2, because u squared over u to the fourth, that would be like having a u squared on the bottom. And so I think it'd be best to write it as 3u to the negative 2 plus 4u to the negative 3. And then we have minus 12u to the negative 4. And again, this is du. That's what we've got there. So this is a great example for me to emphasize that constant multiple rule idea again. So in this problem, a few different times we see constants in front of our variables. Leave the constants there, then do the power rule. So the 3, I ignore the 3 entirely. I add 1 to my exponent, so that becomes u to the negative 1, and I divide by that. So the power rule said add 1 to the exponent, whatever that is, that's what you're dividing by here. And so with this one, the 4 stays, and then I add 1 to the exponent, so that would give me u to the negative 2, and then I divide by that negative 2. So you see that number as the exponent is also what I'm dividing by. That number as the exponent is what I'm dividing by. And the constant is just hanging out as part of the constant multiple rule. And then this one would be minus 12. And then add 1 to the negative 4. That's going to give you u to the negative 3. Divide by negative 3. Okay, so let's clean this up and see what we get. This is going to be, let's see, that negative 1 can come in front. So this would be negative 3 over u to the first. And the 4 over negative 2 becomes minus 2 u to the negative 2, or minus 2 over u squared. And then a negative divided by a negative looks like we'd have plus 4 over u cubed plus c. And I believe, let's see if I did this right, negative 3 over u, I think the answer is B, minus 2 over u squared plus 4 over u cubed plus c. That is correct. Okay, number 3. Find the indefinite integral. And here I'm probably just relying on functions that I'm already familiar with their derivative. And since there's a product, I'm most likely going to just distribute this through and hopefully get some of those functions that look like derivatives of some other functions. And so if we distribute cosecant of y through, then this becomes the integral of 3 cosecant of y cotangent of y. And then we have minus 3 cosecant squared y. And I actually could have left that 3. I could have brought the 3 out in front of this whole thing. So that might not have been a bad idea. But hopefully the way I've written it here doesn't prevent us from being able to answer the question or anything. So I'm saying, what function has cosecant y cotangent y as its derivative? Well, I believe it was cosecant that had a derivative of negative cosecant cotangent. You can look at that table, that chart that you have, and see if you can pick that from there. So cosecant has negative cosecant cotangent as its derivative. So negative cosecant would have positive cosecant cotangent as its derivative. But there's a 3 here, so I think that the antiderivative of this piece is going to be negative 3 cosecant y, because the derivative of cosecant is negative cosecant cotangent. Yep, and that would get me to this, because then the negative would cancel with that negative, and the 3 just goes along for the ride. And then the function that had cosecant squared as its derivative was, I want to say that was negative cotangent, or if you think of this as being a negative cosecant squared, then that's a positive cotangent of y. So I believe that the correct answer here is negative 3 cosecant y plus 3 cotangent y plus c. And so this would be, I think that it's this one right down here. It's E. Okay, moving on to number 4, solve the differential equation. So the way that we typically do that is we bring this to the other side, and so we've got dg is equal to negative 12z cubed minus 4 dz. So if I take the antiderivative of both sides, what function, this is like 1 dg, what function has 1 as its derivative, and that function's in terms of g? Well, that's just the g function. So g would equal the antiderivative of negative 12z cubed minus 4. And so, again, watch how I deal with this negative 12. I just leave it there. It's a constant. And I'm just going to use that power rule. So my emphasis, I want to emphasize this enough that whenever you have a constant in front, you just leave that constant and then just do the power rule. So this is going to be z to the 4th over 4. Because some students will sometimes try to do this all in their head at once and figure out that it's negative 3z to the 4th. Not worth it. I mean, just leave that constant there. Do the basic power rule. It makes your life so much easier. And then this would be minus 4z plus some constant. And so we've got g is equal to negative 3z to the 4th minus 4z plus a constant. And we can plug in the initial condition or the specific condition that we have and arrive at our constant. And so I'm going to plug negative 2 in for z and 5 in for my output. And when we do this, let's see what we get for c. So we get 5 is equal to, that's going to be 16. Negative 2 to the 4th is 16 times negative 3. That's negative 48 plus 8. So I think that's negative 40. So I think that c is going to be equal to 45. And if that's the case, then my specific solution is exactly what I have here, but I'm going to plug 45 in for c. And so I guess that's not the most simplified. So my g of z should be equal to negative 3z to the 4th minus 4z plus 45. And so which choice is that? That looks like it's D. Negative 3z to the 4th minus 4z plus 45. Okay, whoops. Let me get that out of there. And let's go to the very last example here in the practice right now. A ball is thrown vertically upwards from a height of 6 feet with an initial velocity of 60 feet per second. How high will the ball go? Note that the acceleration of the ball is given by acceleration is equal to negative 32 feet per second per second. So if acceleration is equal to negative 32, then velocity is negative 32t plus c, or plus v naught, and position would be, the antiderivative of velocity would be negative 32 times t squared over 2. See how I just left that constant there and then did the antiderivative of the t, plus v naught t plus my initial position. That constant in the position equation is the initial position. So we've got s is equal to negative 16t squared plus v naught t plus s naught. The question is saying how high will the ball go? So if you're trying to determine a height, then doesn't that mean that we need to be working with this position equation? We also know if